We begin our study of free fall by looking at the simplest problem, which is falling without an atmosphere. In other words, falling in a vacuum. And let's decide to call position or altitude y at t. And so this is the position or altitude at time t. At time t. And normally we'll use t seconds. We'll do it in seconds. Now the speed or velocity is the rate of change of position. So y prime of t is also called v at t. This is the velocity at time t. And the second derivative is the derivative of velocity, which is acceleration. So I just abbreviate acceleration there. If we're working in terms of the English units, then we would start off with feet, and then velocity is, let's look at that again. See, y prime is dy dt. The units of position are, in this case, feet, and the units of time, we'll say, are in seconds. Feet per second. Distance over time is velocity. If we want to go with the metric system, then it would be meters per second, perhaps. So these, when you take that first derivative, it changes the units to velocity units, feet per second. And then when we take the second derivative, which is the rate of change of velocity, how fast is speed or velocity changing? And that's called acceleration. And when you look at its units, we have feet over second squared, feet per second squared. So those are the units there. Now, so suppose that we fall from a given height. Suppose that the initial height is y at 0. And we could call that y sub 0, subscript 0 or y naught. And suppose that the initial velocity is v at 0 or v naught, and we have acceleration. So if we're near the Earth's surface, acceleration is going to be constant, and would be given by g, the gravitational acceleration. So in this model, to make it the very simplest, we're going to assume that the gravitational acceleration is constant. And later on in the course, we'll look at the problem where we account for the differences in gravitational acceleration depending upon how far you are away from the center of gravity. And we'll solve that numerically. But for now, let's keep it real simple. And near this Earth's surface, for all practical purposes, the acceleration remains constant. We'll call that g. So if we start off with the only thing acting on this object as far as acceleration is g, then the velocity would be the antiderivative of acceleration with respect to time, and that would be gt plus a constant. Now the constant will be the initial velocity, because if I plug 0 into here, 0 times g is 0 plus my additive constant, that means my v at 0 is my initial velocity, v naught. That's my additive constant. So now I have an expression for velocity, and as far as position, y at t, we'll integrate the velocity function, its antiderivative. So I integrate this, and we'll get g t squared over 2 plus v naught t plus the initial height, y0. So again, when we integrate this, we get an additive constant, and the additive constant, when you plug 0 into the function, would be the initial height. So the model is right here describing position and velocity and acceleration. And if your initial velocity was 0, this term would disappear and the model becomes even simpler. So anyway, it's a very simple model, and I'm counting on that you probably have seen this before somewhere. If not in Calculus 1, then perhaps in a physics somewhere in your background. So let's work my standard problem, which is jumping out at 10,000 feet and seeing what happens. A man falls off a platform 10,000 feet up through a vacuum. And the gravitational pull is, like Earth's, 32 feet per second squared. What is his altitude and velocity after 10 seconds? Alright, so this is sort of my basic problem I want to carry through the other two freefall models so we can compare results. Well, the acceleration is the second derivative of position. So you might say that's A, is y double prime is equal to 32. Now, it's going to be negative 32. But why negative? Because if position is positive going up, then when we fall, the velocity and the acceleration are negative because they're pulling it down. And so up is positive, down is negative. So in this case, actually my acceleration, y double prime, is minus 32 feet per second squared. So that accounts for direction, up and down direction, putting that negative into it. So it means that his velocity is going to calculate as a negative, and until he hits the ground, however, his position will still calculate as a positive. So, well, let's see what happens. So now his initial velocity is 0, isn't it? Because he's just falling off the platform. And so the velocity, which is y prime, I'll integrate negative 32 with respect to time and get minus 32t plus the constant, which is the initial velocity. Because if we plug 0 into this function, we'll get this additive constant, and initial velocity was 0. So there's our velocity, minus 32t. And so already we know we can answer one question. What's his velocity after 10 seconds? Plug 10 into here, it's 320 feet per second going down. We'll write all that up. Now the position would be the antiderivative of velocity, so we're going to integrate negative 32t with respect to time, and we'll get minus 16t squared plus the initial height. And the initial height was 10,000 feet, so when you plug 0 into here, you get 0 plus 10,000. So position is minus 16t squared plus 10,000. There we go. Alright, so let me erase the board and I'll kind of fluff this up a little bit and then we'll write out the answers. So we calculated his velocity, minus 32t. His altitude or height is minus 16t squared plus 10,000. And we wanted to know, well, where is he at after 10 seconds? So after 10 seconds, he has an altitude of, so we'll plug 10 into here. 10 squared is 100 times 16 is 1600. Subtract 1600 from 10,000 and we have 8400. So he's 8400 feet up. So after 10 seconds he has an altitude of 8400 feet and a velocity of I'll plug 10 into here, I'll get, now I'm going to get, technically I'm going to get minus 320, but we assume he's going down, so let's ignore the negative as far as reporting the answer. He's going down at 320 feet per second, so his velocity is 320 feet per second. There we go. So, very, very, very simple problem. And we'll look at this with the other two models falling through the atmosphere, and things will get a little more interesting there. So now I want to add onto this problem another question is how long before he hits the ground and how fast is he going? So let's work that out. So now he's going to hit the ground when y at t is equal to 0. So he hits the ground when y at t, not y at 0, but y at t equals to 0. So if I set minus 16t squared plus 10,000 equals to 0, then 16t squared equals to 10,000, and t is it 25 seconds? Let's see here, 10,000, if I divide by 16, is 625. So t would be the square root of 625. It just, by coincidence, I picked a good number. The square root of 625 is exactly 25. So he hits the ground after 25 seconds and at a speed, or at a velocity. I think speed and velocity are more or less interchangeable in these one-dimensional problems. We'll put 25 into here, and that's pretty fast. 32 times 25 is probably 800. Yeah, velocity of 800 feet per second. Ooh, boy, that's fast. 800 feet per second. Let's see, if I multiply it by 60 and divide by 88, I get miles per hour. That's 545 miles per hour. Okay, it's pretty fast. Not going to be anything left of this poor guy. All right, so now just for the fun of it, I want to mention that around 1960, maybe 62, I think it was 1960, the Air Force, I think it was the Air Force, sent one of their men up in a balloon, weather balloon, up to around 100,000 feet. They had a camera on them. I actually saw the video of this once. Maybe it's on YouTube somewhere. But this volunteer was up pretty much in space. At 100,000 feet up is about 20 miles. It's close to being in space. And in this balloon. And he jumped out of the balloon to see if it's okay. And what the idea was that could astronauts escape from that high up and be okay. Well, this guy lived to tell the tale. He did survive. He had good parachutes. They had planned it very well. And but he is, I guess the legend has it, this man is the only individual to personally have broken the sound barrier and created a sonic boom just with his body. Because at that altitude, he was, for all practical purposes, falling in a vacuum. And so he, after 25 seconds, he's close to the speed of sound. And I don't know what the speed of sound is up there, but it wouldn't take him long before he reached the speed of sound and created his own sonic boom. And so, presumably after that point, he pulled the cord and probably had several parachutes that were required to slow him down. I'm not sure how that worked. I haven't researched it, but it's an interesting story. It's a true story that a man did jump from 100,000 feet up, practically into a vacuum. He also had a spacesuit on, by the way, in case you're wondering. Yeah, he needed a spacesuit in order to breathe up there. All right, so there's our basic problem. And now we'll make it more interesting by introducing atmospheric resistance. And we'll see what happens to these numbers.